Welcome to Lesson 5 of Control Theory. Today, we'll work through another plant modeling example, the RLC parallel circuit. This builds on what we learned with the RC circuit in our previous lesson. In our last video, we modeled an RC circuit using differential equations. We learned how to identify inputs and outputs and how to derive the mathematical model. Now we'll apply the same approach to a more complex circuit with three components, a resistor, capacitor, and inductor, all connected in parallel. Here's our RLC parallel circuit. We have a resistor R, a capacitor C, and an inductor L, all sharing the same two nodes. A current source provides the input current I, and we measure the output voltage V across the parallel combination. The first rule of control engineering is to clearly define our input and output. What do we want to achieve, and with what? We want to control the output voltage V using the input current I. In control notation, input is represented by U and output by Y. So we define U equals I and Y equals V. Now let's analyze the circuit. The main current I enters the parallel combination and splits into three branches. By Kirchhoff's current law, the sum of currents entering a node equals the sum leaving. So, our main current I equals I1 plus I2 plus I3, where each represents the current through the resistor, capacitor, and inductor respectively. Let's find each branch current, starting with I on it through the resistor. In a parallel circuit, all components share the same voltage. The voltage across the resistor equals V, and the other end connects to ground, which is 0 volts. Using Ohm's law, current equals voltage divided by resistance. The voltage difference is V minus 0, which is simply V. Therefore, I1 equals V divided by R. This is the resistor current. Next, let's find I2, the capacitor current. For this, we need to recall the fundamental capacitor relationship. Charge Q equals capacitance C times voltage V. But we need current, not charge. Current is defined as the rate of change of charge over time, so we differentiate both sides of Q equals CV with respect to time. The capacitance C is constant, so it comes out of the derivative. This gives us I2 equals C times dV over dt. The capacitor current depends on how fast the voltage is changing. Finally, let's find I3, the inductor current. For inductors, we use the voltage-current relationship V equals L times di over dt. This tells us the voltage across an inductor depends on how fast the current is changing. But we want current, not voltage. We need to solve for I3. Taking the integral of both sides with respect to time, the derivative and integral cancel on the right side. This gives us I3 equals 1 over L times the integral of V with respect to time. Now we have all three branch currents. Let's write our complete equation. The main current I equals the sum of all branch currents, V over R plus C times dV over dt plus 1 over L times the integral of V dt. There's a problem with this equation. In control theory, we prefer to work with differential equations, not integral differential equations. That integral term makes analysis more difficult. We need to eliminate it. The solution is to differentiate the entire equation with respect to time. When we differentiate an integral, they cancel out. Applying the derivative, di over dt equals 1 over r times dv over dt plus c times d squared v over dt squared plus 1 over l times v. Now we substitute our control variables. Replace v with y for output and I with u for input. This gives us du over dt equals 1 over r times dy over dt plus c times d squared y over dt squared plus 1 over L times y. Rearranging to standard form with output terms on the left, c times y double dot plus 1 over r times y dot plus 1 over L times y equals u dot. This second-order differential equation is our plant model for the RLC parallel circuit. Let's review what we accomplished. We defined the input current and output voltage. We found the current through each component using Ohm's law, capacitor equations, and inductor equations. We combined them using Kirchhoff's law, differentiated to remove the integral, and expressed the final model in standard control form. In the next lesson, we'll learn how to draw block diagrams from these equations. See you then.